Okay, for this podcast, we're going to do some practice determining the concentrations at equilibrium. So we're going to change that first slide. We're not calculating equilibrium constant, we're calculating concentrations. All right, so before I go on and show you how to do all these, I thought I would give you the answers so you can try them all. And if you get the right answers, you have no need to watch the podcast, or you can just fast forward to the ones that you struggled with. Okay, so here's the first one. So let's sort of take this a step at a time in terms of what we did. So the first thing we did was we're told we have 1 atmosphere, and we want to know the equilibrium pressures of both the reactant and the product. So we set up an ICE table. We're told we have 1 atmosphere of I2. So the assumption we're going to make is that we have no product, no I. So based on the coefficients in the reaction, we're going to take minus x here, plus 2x here. This gives us 1 minus 2x. This is 2x, okay? So we're going to take that 2x squared over 1 minus x is equal to the equilibrium constant. Because our equilibrium constant is so low, we're going to eliminate x because we are the small k tells us that we are reactants favored, so our assumption is we're not going to lose much reactants. We're going to end up close to the same concentration. So when we do that, we end up with 4x squared is equal to 7.275 times 10 to the minus 5. Okay, so if we divide this by 4, we get 7.275 times 10 to the minus 5. And then we take the square root of that, we end up with 0.00853. So to find the concentration of I2, we're going to take 1 minus that concentration, which gives us 0.991. We do the same thing with the I. We're going to have 2x, x being 0.00853 gives us a concentration of 0.0171 atmosphere of I. Alright, let's take a look at the next problem. Okay, the equilibrium constant for a given reaction is 0.561. If the initial concentration is 0.5 molar, what are the equilibrium concentrations of each species? Alright, so we're going to start with the Rice table. In here it talks about the concentration of HI, and the HI is, we know the concentration is 0.5 molar. Doesn't mention the reactant, so we're going to assume that those are small, and we are going to put them in as 0, right? They don't mention them, so we're going to assume they're 0. So what's going to happen here is we have all products, so the product is going to be decomposed into reactants. So I'm going to lose product. It's going to be 0.5 minus 2x, and gain reactants, x and x for each of the H2 and the I2. So we're going to end up with the equilibrium constant is equal to 0.5 minus 2x over, and that's all squared because of the 2 in the coefficient, and that's all over H2 times I2, which is x squared. Now when we looked at this x is not something we can drop, because this equilibrium constant is not insignificant, okay? So, but what we can do is we have a square term on the top and a square term on the bottom. So what we can do is take the square root of both sides, and when we do that, we end up with 5 minus 2x over x is equal to the square root of 0.561, which is 0.749. We solve for x, and when we do that, we get x is 0.0182, which is the concentration of H2 and I2. To get the concentration of HI, we're going to take 0.5 minus 2 times x, and when we do that, we get a concentration of 0.464 molar of HI. Okay. Alright, for this one, I'm going to switch my pen to red now. I have initial pressure of 1 atmosphere, and we want to know the equilibrium pressure of I2 and I, and we're given the equilibrium expression. Okay, so we're going to set up a rice table. We're told the initial pressure of I2, and I is not mentioned, so we're going to assume we have all reactant to start and no product, so that will make that 0. The I2 loses X. I gains 2X because of its coefficient. So at equilibrium, I2 is 1 minus X, and I is 2X. Okay, so if we do this, we end up with the equilibrium constant is equal to 2x, which is squared in the numerator, over 1 minus x in the denominator for the I2 concentration. Because Kp is tiny, we're going to go ahead and eliminate x from the equation. So when we do that, we end up with the equilibrium constant is equal to 2x squared. When I square 2x, I get 4x squared is equal to the equilibrium constant. So in order to solve for this, I'm going to take the square root of both sides, and so 2x squared is 4x squared. I take the square root of that, and this first I divide both sides by 4, and then I take the square root. And when I do that, I end up with x is equal to 0.038. I just want to do a confirmation that 0.038 is insignificant, because that k is kind of on the borderline, right? So 1 minus 0.038, or 0.038 over 1 is 3.8%, which is below the 5%, so yes, it's insignificant. Alright, so once I have the 3.8, I can fit it into the equilibrium, and concentrations in what I have for I2 is 1 minus 0.038, gives me 0.973 molar. And for I have 2 times x, which is 0.038, and that gives me 0.0539 molar. Okay, we're going to do one more. This is an important one because it's a little bit different. Okay, so here we have N2O4 placed into our reaction vessel at a concentration of 2.5. What is the NO2 concentration at equilibrium? So I'm starting with all product from the way this reaction is written and from the Kc that I'm given. Okay, and I have no reactant to start, so I'm going to lose some concentration of my product and gain some concentration of my reactant. So my equilibrium concentrations are here, 2x and 2.5 minus x. So if I write my expression, it's the Kp, or the Kc, is equal to 2.5 for my product minus x over 2x squared due to the coefficient, right? Now, I look at this and I say that, can I eliminate that x? My k is huge, right? It's not insignificant, but we got to think about this in reverse. Because what I'm doing is I'm putting N2O4 into the reaction vessel. That, it sounds like I'm putting a reactant in, and that's really essentially what I'm doing. This is written as a product here, but in fact what is happening is this product is becoming 2NO2, right? But because the K is so large, what that tells me is the reaction is product favored. So very little of that product is going to decompose and become NO2. So the opposite is true. In this case, if my K is really, really large, that means I am product favored, and very little of that product is going to be gone after the reaction has reached equilibrium. So because my K is really large, I can eliminate my x. Okay, so now I have 2.5 over 2x squared is equal to 87.2. Okay, I solve for x and I get x is equal to 0.0847. Do a little confirmation check to make sure it's less than 5% of the original 2.5 molar, and it is. It's only 3.4%. I calculate my equilibrium concentration based on my 2x here for NO2, and I get 0.169 molar for NO2. Do the same thing with N2O4, and I end up with 2.41 molar of N2O4. Okay.